So, our first exploration of real material. And in this section, we are not particularly interested in directionality of temperature, hot or cold. We're looking at the response to any change in temperature and what it means to consider that we need to change temperature. We'll even think about what temperature is. This is fundamentals of temperature regulation. So recall from last week, our introduction, that we're looking at the interface between our person and the environment, ourselves and the environment. And we spent some time trying to articulate what the environment is. From the point of view of temperature regulation and heat, the environment is the sum total of all conditions, hot or cold, elements in the immediate surroundings that will influence, in this case, the temperature, the heat gain or the heat loss of the individual. So we don't know yet what those elements are, but there are a finite number of them, and we can define them, we can measure them, and we can actually calculate the likelihood that someone will gain or lose heat. It's a complicated calculation, but we can do that. We're looking at it more in principle right now and throughout the course. It will be a principle. You won't have to do an equation where you calculate heat balance. Overall, this section, the next 2-3 weeks, I think I've already mentioned this, but we focus mostly on temperature for the first half, mostly on pressure for the second half, and then we add in a few elements near the end and some activities that vary the topic somewhat. But hyper and hypothermia, hyper and hypobaria, the main focuses of this course. This section, though, only the thermal environments that we're looking at. So all conditions that have an impact on the organism, but that are not part of the organism. Think about it that way. On the organism, but that are not part of the organism. So if we are studying one organism in the context of its environment, this is really ecology. A whole other branch of science that deals with the relationships of a biological organism in its environment. We're really studying ecology. That's what environmental exercise physiology is. It's ecology with humans as the subject and exercise as the action. And ecology dictates that whatever the organism is, it's at the center of its environment, and we are measuring the sum total of all factors on that central organism. Depending on the organism, it might resist those external factors, or it might not. So ecology is a much more broad study of different types of organisms in their ecosystem. We are pinpointing humans at the center of that ecosystem. So as we take this short tangent, let's consider what it means to be an organism at the center of your environment. A human, a frog, a rodent, which incidentally we found over in West Street yesterday. There's a nice video circulating about it. Dr. McKenzie was indisposed at the time and it jumped out at him. They both nearly had a hernia, I think. Rodents, frogs, humans, what does it mean to be at the center of your ecosystem? In broad strokes, there are two classes of organism in the study of ecology. We could be either a conforming organism or a regulating organism. And conforming organisms are those that do not resist the impacts of the external environment. In fact, their internal conditions are dependent on the external environment. They're closely related to the conditions of the external environment. And so if the heat goes up around them, their body heat will go up as well. And we contrast that with regulating organisms that are generally resistant to changes in their surroundings. Even though heat can go up, heat can go down in their surrounding environment, their internal temperature remains relatively stable. Within limits, of course. There are extremes where their internal temperature will eventually change. But over some narrow range, it remains relatively stable. We call this term homeostasis, keeping things in balance, keeping a nominal temperature. And so, in your opinion, which class would we as humans fall into? Are we conforming or regulating? And you can probably guess just by looking at one word on that slide that you might have heard in A&P a number of times.
Regulating.
Regulating, fantastic. Homeostasis, that is the balance that we try to maintain always within the body: blood pressure, temperature, ion flow, ATP use. We want these things to remain at some certain level. If they change, we restore that level. So we are regulating organisms. We resist changes in the external environment. To illustrate this point, let's consider what a certain variable might do in response to changes in the environment. Here you can think of this as temperature. You can think of it as O2 saturation or any other thing. In this example, let's consider the internal environment as temperature. A conforming organism will change readily and quickly with a change in the external environment. So as this goes up to the right, the internal environment also increases in a conforming organism. And these are what we typically call cold-blooded animals, cold-blooded organisms. The more correct term is what we call poikilotherms, which is a harder word to say. Cold-blooded gets the same point across. That is, they have little ability to generate their own heat. They rely on the heat radiating from a hot rock or from hot, humid air in their surroundings. Because they're conforming and their internal environment changes quickly, if you were to measure their internal environment at multiple different time points, you'd probably see a pretty wide variation, right? If this green line overlapping the dots is where that organism is alive, it changes a lot. There's a low value and a high value, and anywhere in between that organism is alive, it's variable. Their internal environment is variable. And generally outside of this range, survivability isn't an option. So the internal environment is variable, but they have little tolerance for any trips outside of that narrow range, whatever it might be. And it's probably exaggerated here. This long green line is a little bit larger, I would expect, than a lot of poikilotherms would exhibit. Outside of that range, they wouldn't survive. And this is why a lot of these organisms live in environments that are typically tropical, where the environment is stable, where there isn't a lot of internal variation. The range depends on the organism, depends on the environment, but a lot of these have pretty narrow ranges and therefore can't survive with this large fluctuation in internal temperature. Here, this organism can only live within the red band in this case. We don't have degrees, we don't have humidity, we don't have any of like altitude data, we don't know the environment, but there's some finite range outside of which it can't survive. Nova Scotia in the winter is probably over here somewhere. So this is the easiest concept to get across. Surrounding temperature goes up, conforming organism temperature goes up as well. What about a regulating organism that resists changes in their external environment? And these are what we consider warm-blooded animals. They have their own internal sources of heat generation. They can modify those internal sources of heat generation. Turn them up when it's cold, turn them down when it's warm, to maintain a stable internal environment. A stable internal environment. And what I mean by stable is that whereas on the last slide we saw the y-axis, the internal environment varied over a wide vertical range, the internal environment here is generally flat. It's generally flat. We don't know the reasons why the internal environment is maintained, just that it is maintained at this point. And what this means is that the wider the zone of stability, the wider the variation in external environment that we, or these organisms, can maintain or can, what's the word I'm looking for? Can survive in? It's not the word I'm looking for, but you get the idea. The wider the range of acceptable environments. And so immediately, if we look at this stable range, this is ideal, this is homeostasis, where everything is maintained at some ideal level. Well, we are fine and dandy living within this range. Any environment that allows us to maintain this stable level is what we would call ideal. There's no stress, there's no concern about living in those environments. And where regulating organisms differ from conforming organisms is that there's no cutoff. It's not an immediate cutoff. There's more of a spectrum or a transition. So these bordering regions aren't incompatible with life. We just simply need to, or we attempt to regulate our internal temperature more. We fail at doing so because it does change. It goes down on the left-hand side of the graph. It goes up on the right-hand side of the graph. But it's not immediately incompatible with life. So there's an ideal range in the middle. There's a non-ideal range on the borders, but in which we can survive. And then outside of that, as we get to further extremes, there are situations where it's incompatible with life. We can't live in really hot or really high altitudes. There are extremes where even where even regulating organisms cannot survive. Now we have an idea of what this means for us. We have an idea of what temperatures are comfortable, what altitudes are comfortable. And this window, we could probably put degrees Celsius values on here if we wanted to. The window changes for other organisms as well. It can shift up or down depending on where they've evolved. But these regulating organisms are the masters of their domain. They are making the environment work for them by regulating internally. So let's bring it back away from ecology and actually put numbers on this. Humans can only survive within a narrow range, hence the background on this slide. If we were allowed to choose, we would like our body temperature to be at 37 degrees Celsius plus or minus 1 degree tops. This is what we would call ideal body temperature. And for the most part, we are pretty good at maintaining this body temperature. We don't know how we measure core temperature yet. We'll talk about that later. But if I were to measure core temperature in all of you, the average would be very close to 37 degrees Celsius. Despite that, depending on the environments that we're in currently or the exercise activities that we undertake, there is a range of what we call acceptable temperatures. We want temperature to remain at 37 degrees. If our body temperature is 35, 36, though, we are okay with that. It's acceptable. We can survive and regulate within this range. We are in no danger of losing normal function within the range of 35 to 40 degrees Celsius. You might feel warm or cold. You might want to put a jacket on. You might wear a jacket to lecture like I did today because Thursday was cold and I was almost shivering up here. But we don't have a problem surviving within this range. Outside of this range, if we spend too much time outside of this range, let's put it that way, we would consider that an unacceptable human body temperature. Now, in your mind, what would constitute unacceptable? What does that mean? How do you picture that? Catastrophic failure? If we're okay within the narrow range of 35 to 40 degrees Celsius, if that's acceptable, what does it mean to describe anything outside of this range as unacceptable? What do I mean by unacceptable? Any ideas? Just a thought exploration. There's no wrong answers yet. Not acceptable. Something is not acceptable. What's unacceptable about being outside of that temperature range? What would it look like? What if my body temperature was 41? What would happen? We don't know specifics, but imagine. Melt, disintegrate, drop dead. Those are extreme ideas, right? So in the extreme sense, I'd call that unacceptable. Is there somewhere between normal acceptable temperature now and that point? Yeah. How would you describe that range, that spectrum? Moving between acceptable to that extreme. What would happen?
The symptoms that don't require serious medical attention.
Okay, so I'm developing symptoms of an underlying condition that don't seem to need urgent medical attention, but would they eventually? Okay, they would eventually. They might progress and get worse. There might be a progressive deterioration of function. Proteins in your body might start to unravel. Your heart might get weaker and weaker and weaker. You might not be able to prevent the increase in core temperature. What I want to get across is that this unacceptable, the idea of unacceptable, isn't a threshold where if you step through, you collapse. It's a progressive loss of function. And I think importantly, the body tries to do everything that it can to recover function, but it doesn't have the capacity. It doesn't have the ability to fight off the external environment in those unacceptable cases. So that's just how I want to color that idea of unacceptable. In contrast, acceptable means that I have the capacity. If my body temperature is 35 degrees, I have the ability to try to warm myself and prevent it from getting colder. I can live within that range. It's acceptable. Unacceptable outside of this range, I don't have the capacity physically to maintain normal body temperature. It gets worse and worse and worse until eventually I'll fail. So this is a pretty narrow range. Consider that outside, what is it today, -10 degrees Celsius, and we want to maintain plus 37 degrees Celsius internal temperature. 47 degrees difference between what's happening outside and what's happening in here. On the other end of the spectrum, we don't really get too far outside of the spectrum, but we approach body temperature in the summer months. Certainly the winter is a really good example of where there's a discrepancy between internal and external conditions. So we have to constantly regulate and try to maintain body temperature, and we're pretty limited compared to some other organisms. We don't have a lot of fur, we don't have blubber to insulate, we don't hibernate, we don't have some of these physical temperature regulation mechanisms, but we do have an advantage where other organisms don't in our behavior, and technological countermeasures are certainly above and beyond the other organisms that live on Earth currently. So we have clothing that we can use. We've developed central heating. There's a lot of behavioral aspects that allow us to regulate within this range and not succumb immediately to -10 degrees outside. So we'll learn more about these processes, but we're contrasting, we're isolating and setting ourselves apart from other regulating organisms and other mammals. Humans are unique in that respect. So this idea of maintaining an internal body temperature of 37 degrees is really all about balance. Homeostasis is all about balance. You've learned that, I think, at length in anatomy and physiology, if not somewhere else. So we have to balance the internal loads and the external loads. If it's hot outside, we don't need to generate as much body heat. If it's cold outside, we need to generate a lot more. And we have a pretty large capacity to generate heat, which is why we've started to thrive in Canada up north where it gets cold in the winter. We typically will measure heat flow or heat balance, the exchange of heat between us and the environment in watts. And you've seen watts before. Watts is what we use to describe a workload as well. Watts is simply a rate of energy. Joules per second, that is 1 watt. 1 joule per second is a watt. So during exercise, you are performing work at a certain rate. Right now, we're generating heat energy at a certain rate. The environment is trying to take that energy from us at a certain rate, and we would describe all of those in watts. So if we think about heat energy, sitting here quietly, you are maybe getting a little bit colder, but you're able to maintain a relatively normal temperature. You're producing heat at roughly the rate of 100 watts. If you got up and walked around, or if we measured my heat production, it might be slightly higher, probably not to this level, but if you're walking to your next class, maybe 300-ish watts of energy produced. If you were then to exercise and we measured the amount of heat energy produced, it could be in the thousands. Thousands of watts of heat energy produced. Is this appropriate? Are these, I would imagine these numbers are probably not sitting well with you. Sitting at rest, you're producing 100 watts of energy. What's a typical workload? A typical moderate intensity workload as you learned in XPhys? If I wanted to put someone on the cycle ergometer at 60% of VO2 max or 60% of VO2 reserve, approximately what kind of workload are you looking at? Doesn't matter the fitness or sex, let's ballpark it. What kind of workload are you looking at? 60% of your aerobic capacity.
2
KPM, okay, so you're thinking kiloponds, which are the weight or the resistance on the bikes. Do you remember how to get to watts from KPM on those Monarch bikes? KPM is a crucial part of that equation, and you also need the cadence, RPMs. So the work you're doing is how much resistance are you cycling against and how fast are you cycling. So if you had 2 KPM and you were cycling at 60 RPM, it'd be 120 watts. 2 times 60, 120 watts. And that's probably even on the low end. I would ballpark it maybe at 150. If you have a more fit individual, 200 watts, that'd be 60% of your aerobic capacity. But you're doing 100 watts at rest. Are you exercising sitting there? Why are these numbers off? These are higher than we're used to thinking. 280 to 350 watts while walking, that's way too high. That's 85% of VO2 max. Why are these numbers so much higher than the numbers that you've seen in XPhys? There's one important concept that you might have learned about in XPhys. It's the argument Lance Armstrong used to try to claim that he wasn't doping. Or one of them. Where am I measuring this rate of energy? If I'm producing heat energy, where is that happening? And it's not a trick question. Skin, okay. Could be the skin. Could be contained within the skin. It's in the body. You'd feel it at the skin. You'd feel the heat being produced at the skin. The organs in the body, the muscles in the body, your body as a whole is generating this heat energy. Where is the work being performed when you set the intensity on one of the ergometers? Inside or outside of your body? I think I heard it. It's not a hard question. Outside? Yeah. This is heat being produced inside your body. Any intensity that you set on the bikes across the way is work being accomplished externally. And so what's the important idea or concept relating internal work and external work? Do you remember this from XPhys? It's not one-to-one. In fact, it's way off. What am I describing? What phenomenon? Percent something. Percent efficiency, thank you very much. Percent efficiency, absolutely. We waste so much energy internally to accomplish a relatively lower workload outside of the body. We're about 20 or 30% efficient. And what that means is 20 or 30% of the energy we expend internally is used to accomplish work externally. So if we expend 1,000 watts internally, if we're producing 1,000 watts of energy, we're doing 200 to 300 watts of work on the bike. Percent efficiency, that's the key concept that explains why these numbers are so far off of what we're used to. if I'm generating 1,000 watts of internal energy, I can only do 200 watts on the bike, 300 watts on the bike, tops. The rest is wasted. The rest dissipated as heat. 700 to 800 watts, if I'm exercising, is dissipated as heat. That's why you heat up during exercise. You're inefficient. Bad for Olympians, but really good for the obesity epidemic, right? You want to waste internal energy as much as you can. All right, let's leave that concept there. That's why these numbers are so far off. They're a lot higher than you're used to. It's not 280 to 350 watts that describes the act of walking. It might be 80 to 100 tops, but it's the efficiency, the idea of efficiency that describes that discrepancy. So humans are 20 to 30% efficient, and that's it. The rest is dissipated as heat. Now, let's talk about this idea of balance, and more specifically, sensing this heat balance. You have something like this on the slides online. There isn't a lot filled in, but this is a typical feedback loop. You've learned about feedback loops before. You have information coming from the periphery or coming from the edges of the system that's being fed into some central controller. It says, okay, I have this information coming in. Is it as expected? If it's not as expected, I need to create a plan. I need to change something to bring it back in line with what I expect to happen at the periphery. So let's go through an example where we are trying to regulate temperature. We have typically sensors in the skin and in the core. And if there's a fire nearby, if the rad gets turned on to full blast, if the room gets hot for some reason, we sense that. These are temperature sensors in the skin and in the core that are always trying to sense and maintain body temperature within that range. Ideally 37, 35 to 40 if nothing else. But we're trying to maintain temperature within that range. If we are presented with a stress that wants to push us outside of that range, these sensors will sound the alarm bells, will let us know that there is an external stress that is endangering our internal environment. In this case, we're getting too hot. These tell our central integration centers, hold on, my skin's really warm. I need to do something to prevent that. Maybe I lift my hand out of the way so I don't burn it over the element or burn it in a flame. Maybe I do something else. Whatever that something else is, whatever that response is, happens, and then I check back in. Okay, am I still registering a higher than normal temperature at the skin? Am I still registering a higher than normal temperature in the core? If so, do whatever you did again. Keep doing it. Do more of it. Try to regulate back down to 37 degrees Celsius. So what are some things that you might do if you were hot to cool yourself? Have a drink of water. Have a drink of cold water. Absolutely. What else might you do if you're hot?
Remove a layer of clothing.
Remove a layer of clothing. Fantastic. These are all things that I don't have on the list I'm going to put up next. Remove a layer of clothing. Try to remove the insulation. What else might you do to cool yourself?
Rub an ice cube on your arm.
Okay. Rub an ice cube on your arm is an example of how we describe that. You're essentially trying to reduce the influence of whatever this hot thing is. You're removing yourself from the heat, or you're disrupting the pathway of the heat into your body. You're making your body cool. You're trying to artificially remove this heat source. It's very similar to the idea of removing a layer of clothing, but you're disrupting it in a slightly different way. Great idea. Rub ice cubes on your skin. Have a cold shower. Have a cold drink. Remove a layer of clothing. What are some things the body might do? So far, most of those are behavioral. You made a conscious choice to do that. What are some things that the body might do unconsciously? Do you have any idea? Sweat. Fantastic. You might sweat. Sweat is how we lose heat through evaporation. And there's a whole lot of stuff coming up about sweat in 1 or 2 sections. What else might you do? Vasodilation. Fantastic answer. Absolutely. And what we mean by that is send hot blood to the surface so that you can lose heat to the environment, if possible. There's a whole host of considerations. If you're in a really hot room, you might gain heat by doing that, but generally that practice is well accepted. Take your hot blood that's in your body, put it at the skin, and see if you can't lose some of that heat to the environment. Absolutely. Okay, I did have a couple of those on the list. Sweating, removing clothing, take a drink. This increased skin blood flow is the idea of vasodilation. And then pacing. If you were exercising and you got hot, you could slow down. You could, that's pretty much it. You could slow down, you could stop, you could take a breather. These are a few of the things that you might choose to do or that might happen naturally to help cool yourself. All of those would go towards reducing whatever this heat stimulus is, perhaps. Now, I just want to take a minute to prompt you to think about these sensors quickly and just relate them to your own experience. The idea of a sensor is usually it's on or off. It's very binary. The skin temperature sensor detects heat and then sends a signal. The core sensor, if it gets too hot, it sends a signal. But appreciate how many sensors there must be. There's sensors all over the skin. You're sleeping, for instance. Sometimes you really like feet out of the blankets. Your feet are cold, but the rest of your body is warm. How do you reconcile the idea of the skin as one organ sending temperature signals to one central integrating center? And for that matter, where do we measure core? What is core? Is it heart temperature? Is it intestines? Is it muscular temperature? Is it in the torso? And which is more important? Usually, core is more vitally important in that your internal organs need to stay operating at some specific temperature. If they vary, then they're in danger of failing, and that's bad. If your skin, if your limbs, if the muscles change in temperature, it's less bad. So usually core is more important. Also consider, do you have to wait until it gets too hot or too cold? I thought about this when last night I took my dog out just to go to the bathroom before bed, and no one wants to go outside that late at night in the dark. It's freezing cold. You bundle up with 2 jackets, and I get outside, and I know it's cold. I can feel that it's cold on my hands and on my face, and I want to start getting warmer. But in those 30 seconds that I've stepped outside, I'm not cold yet. So I'm already getting signals that are early warning signals to say, if you stay in this scenario, you're going to get cold. How is that possible? If these are typical sensors, and I'm getting a signal right away, maybe I'm not only measuring levels, maybe I'm measuring rate of change, how quickly heat is escaping or how quickly I'm gaining heat. So there's been a lot that I've talked about here, and we'll come back to it later. You don't need to frantically copy down notes and things like that. I just want you to start to think and appreciate how the system might work and some of the nuances of this system. Okay. This is nothing new. The sum total of all the elements in the environment. The thermal environment is what I'm going to use as a basis for the equation we're going to present. The heat balance equation that describes whether you're going to gain or lose heat. So in words, I'm thinking of this as a biophysical aggregate. The biological components being your body, the physical components being buildings around you, wind, water, etc., of air temperature, wind, humidity, radiation, everything in your environment that changes all the time, constantly, and how that impacts the body's thermal environment. In words, I'm describing it like this, and you have an idea of what the thermal environment is already from our discussion at length today and last week. In pictorial form, the thermal environment looks something like this. This really highlights the interface between the body and the environment, or how the body interacts with its immediate environment. This diagram shows thermal balance, all of the elements involved in thermal balance. You have some elements that typically work to heat the body. They are solar radiation, always heats the body. Any reflected or stored radiation off of the snow as you walk outside, off of buildings, concrete buildings, and a downtown core. Not here. If you're ever in a busy city, you can feel that reflected solar radiation. Or muscle contraction, a very inefficient process that tends to heat the body. On the other hand, the elements that would cool the body are convection, the movement of heat away from the body, conduction, the transfer of heat between media, evaporation, like Ali mentioned, sweating, evaporating, removing heat from the skin through evaporation of sweat, and sometimes heat can radiate away from the body as well, albeit it's a much smaller influence than the radiation coming at us from the sun, but there are some electromagnetic waves that can radiate from the body as well. And I haven't highlighted specifically evaporation from airways because it's not typically a major route of heat loss in humans. It is in dogs. If you've seen dogs panting, that's their major way of thermoregulating. There is some effect in humans at altitude where the air is very dry and it's very cold. But for us, it's not a major concern. So I'm leaving this off of the equation right now. These are all of the elements that contribute to heat balance. And if one set is of a larger magnitude than the other set, it dictates whether you gain or lose heat. So if you add up all of the red boxes and their wattage, their number in watts is larger than the number in watts for all of the blue boxes, you will gain heat. You will get hotter, and vice versa. What we are describing, and I don't put this up to scare you off, is the first law of thermodynamics. Energy cannot be created or destroyed. Energy is conserved. Whether you gain or lose heat is simply the transfer of heat from some other space in time. If we consider the system, on that last slide, the system is the body and the environment. The entire system altogether, the energy in that system is always constant. There might be a little bit more of it in the person. There might be a little more of it in the environment. But in that system as a whole, it's always constant. If the energy gained or lost by one component can be observed, that's equal to the energy gained or lost by all of the rest of the components. And so heat balance, as we calculate it for the body, is simply derived from this principle. If we are getting colder, it means that something around us is getting warmer. This is a relatively simple concept, and I know some people will see math or equations or physics, but just think about this in words. There's no need to be scared off, I suppose, by this idea. So let's consider the heat balance equation. And this isn't going to make a lot of sense right now. But as written, this is the sum total of all of the environmental factors and how they would affect the body. Before we explore this, this is a heat balance equation. And I'm curious, what's heat? How would you ever describe heat? In a big picture theoretical kind of way, or you can go into details at the molecular level. How would you describe heat to someone that's never had experience with it? What's heat? We all have an intimate sense of what it is. You can say that's heat or that's not heat. How would you put it into words? What is heat? It's tricky. It is tricky. Heat is if something is hot. Heat is a high temperature. Temperature is the measurement of heat. But what's heat? What is it measuring? Energy. Energy is a great way to describe it. What is energized? Okay. Air molecules, if you're measuring the temperature of the air, you're measuring the energy of the air molecules. That's actually a really good answer. It's the movement or the vibration of the air molecules. If you measure the temperature of liquid or heat stored in liquid, it's the movement or vibration of liquid molecules. As water turns into ice, it's not a magic phenomenon, it's just that all of the water molecules slow down, and as they slow down, they're able to line up in a very ordered pattern, and that ordered pattern results in ice. It all describes the movement of molecules. So heat in the body is a measure of all of the body's molecules and how excited they are, how much energy they have. Our muscle proteins moving. Think about metabolism. You've seen glycolysis and the TCA cycle and fat metabolism, and there's all these enzymes and precursor products, substrates and products. Everything's moving through metabolic pathways. That movement generates heat. That movement, if it's moving fast, is hot. Heat is how much movement of molecules there is. Temperature is a measurement of that vibration or movement of molecules. And so the heat balance equation describes how likely is it the molecules of the body will start to move more or less quickly. Everything boils down to this term over on the left. This S represents the rate of heat gain or of heat loss. The tendency for heat to go up or heat to go down. That is the tendency for the molecules to start to move faster or to slow down. That's all this equation is describing. The rate of heat gain or heat loss. If all of these mysterious factors on the right-hand side are smaller or below zero, if they're negative, that indicates there's a tendency for heat to be lost. The vibration of the molecules is going down. If all of the elements on the right-hand side are positive, above zero, and large, then the rate of heat gain says that the molecules are more likely to start to vibrate faster and faster. So heat balance. I find a way to think about this that's easy to access for a lot of incoming students is to think of it like protein balance. Proteins are always being turned over. You gain muscle mass if protein balance is positive. You lose muscle mass if protein balance is negative. Same thing with heat balance. You gain heat if it's positive. You lose heat if it's negative. Let's consider these elements. And I think what we'll do is go through these elements and wrap it up. We're here till 11. We got 20 minutes, but this has been a lengthy discussion, and this is enough of a large concept that we can leave it after discussing the equation and then get into the particulars on Thursday. So M, metabolism. Metabolism is always positive. Metabolism is the heat produced as a result of enzymatic reactions in the body. And maybe those enzymatic reactions and those metabolic pathways are moving fast because you're exercising. But they're always contributing heat. Because they're moving, they're always likely to excite the molecules around those pathways. Metabolism is always positive. It's an exothermic process. It gives off heat. Metabolism here will describe resting, basal metabolism, and any voluntary work that you're doing to exercise. That's metabolism. Often associated with metabolism is W, which is work, the external work performed. And this is a tricky concept, but it's good that we discussed efficiency earlier, because I think that makes this concept a bit more accessible. The external work performed, I say it's typically negative, but it's almost always negative. If you're using energy to do work, you're not using energy to make heat. In the example where if you were generating 1,000 watts of metabolic heat and you were accomplishing 200 watts of work, well, that's 200 watts that aren't being diverted to making your body hotter. That's taking away from the total. You perform work. Work doesn't often perform you. That's why it's always, almost always, negative. In this case, energy goes towards doing a task, to performing something. It doesn't go towards making your body hotter. This energy was infused into the bike pedals. It made the flywheel spin faster. This energy made you jump on the treadmill, tread? Roll? What's the name for the thing that moves on the treadmill? Belt. Yeah, that's simple. Absolutely. Jump on the treadmill belt and move yourself, propel yourself forward. That was work done that took away from the metabolic heat production that you produced internally. So work is always negative. The last few are simply the equation form of the items on that diagram. Radiation is the sum total of radiative heat exchange. This is electromagnetic wave transfer between your body and the environment. This can be positive or negative. If it's cold outside, you will radiate heat from your body to the surroundings. If it's warm outside, if there's infrared radiation stored up in cement buildings, it will radiate onto you. This can be positive or negative depending on the scenario. And I'll show you some really interesting data that tested radiation and how it affects exercise performance. Not in the X-ray sense, but just in the solar heat sense, like using grow lights, not X-rays. We often think about conduction and convection together. Conduction is C, convection is K. And I don't really have an easy way for you to remember that other than convection in German, I think, starts with a K, and that's why its letter is K. I think the V is angular and the K is angular. However you remember it, both of these work together. It's really hard to separate them. And they describe the energy transfer between media. What do I mean by media? It's transfer between your body and air as a medium, your body and liquid as a medium, or your body and solids as a medium. Those are the media. Conduction and convection describe energy exchange between media. This can be positive or negative as well. Let's talk about conduction. Conduction is easy. Conduction is the fastest, or the situation where there is the fastest transfer. Solid items where molecules are close together, tightly arranged, means conduction can move a lot of energy quickly. Always from high to low. I think that's obvious. From a high temperature or a disordered state to low temperature or an ordered state. High to low. High pressure to low pressure. High heat to low heat. Conduction between your fingers and a cold block of steel that's been left outside, or the desk, which is kind of cool because it's sitting in this cold room. I'm losing heat from my body to this desk. That is conduction. And that's pretty straightforward. Where convection differs, I don't have anything, I guess I have air. I was going to think maybe liquid is a good next step. If I leave my hand in the open air, heat from my hand is moving into this air. And because it's transferring between media, the movement from my hand into the air is an example of conduction. I'm conducting heat into the air molecules. But air can move. The desk couldn't move. My hand was always in the same spot. I would heat this spot on the desk up until it became the same heat as my hand, and then I'd be in equilibrium. Here, the air feels a little cooler. I'm conducting heat into the air, and then convection is movement of that medium. Convection is movement or renewal of that medium. I've moved my own heat into the air, and then by moving that warm air out of the way, I make room for cold air to come in and take its place, and then that movement can occur again. And it can occur as many times as I want, as many times as I renew that supply of air in contact with my hand. Same thing with water. If you put your hand in stable water, you'll feel the water warm up. If you put it in running water, it always feels cold because you're renewing that medium. And that's the difference. Convection describes the renewal of that medium. Conduction is the movement into that medium. Lastly, evaporation, always negative. Evaporation is an endothermic process. Endothermic meaning it needs an input of energy from somewhere. And that input of energy comes from the body. So we secrete fluid out onto the skin. For it to evaporate, it needs energy for the evaporation process to occur, and the immediate source of energy is the skin itself. Makes the skin cooler, removes some heat from the body. Evaporation is always negative. Collectively, metabolism sits apart, but these physical elements, so these are what we would call the bio elements of the biophysical aggregate. These physical elements are grouped generally into what we call dry and wet heat exchange. Wet is fairly obvious because fluid is required for evaporation. Dry is everything else: radiation, conduction, convection. So you might often see something reported as dry heat exchange or wet heat exchange, and this is what it means. Now I think I included the next little pop-up on your slide as well. This is already complicated, and I'll tell you right now, to hopefully quell your fears, you're not ever going to put numbers into this equation, or you don't have to calculate metabolism, you don't have to calculate convection, and then satisfy the equation to figure out heat flow. You won't have to do that. What I want you to take from this is the principle. Metabolism adds the likelihood or increases heat flow. Work decreases heat flow. Depending on the environment, conduction and convection can either add to or take away from heat flow. This is already complicated, but I think it's worth mentioning because I talked about the respiratory pathway in the last slide. It can be modified by the respiratory elements as well. You do have the ability to evaporate fluid from inside the lungs. That's what dogs are doing when they pant. If you're breathing really heavily, you might lose heat through evaporation, not from sweat on the skin, but from the inside of your lungs. And depending on the temperature of the air, you may or may not lose heat. If cold air comes in, that air needs to be warmed, and that warming occurs from heat being transferred from the lungs to that air. So there is a conduction component and an evaporation component in the lungs proper, but for our purposes, we are removing this. We are not considering this in the equation. We're looking only at these 5 main factors and how they 5 main factors and how they affect heat balance. Here, C includes both conduction and convection. That's where my brief pause originated from. So I know today's been, we've talked in depth and in we've had some theoretical examples about what heat is, and it's not a typical exercise physiology class, but at least for me personally, it helps to understand the phenomena, and I hope that maybe it helps you understand the phenomena as well. We'll move into a few more specific examples and more detail about each of these, because it's a pretty important concept for our class moving forward. And then we talk about specifically situations with high heat balance or low heat balance and heat loss. What happens? What does the body do to survive in those situations? So we'll come back to class Thursday, try to make our way through a lot more of these notes, but we might spill over into next week, and then we get into heat stress specifically. Okay, so let's call it there. Have a wonderful Tuesday, and I'll see you in 2 days.